And the first is this Laplace and Poisson equation. Your text actually didn't discuss too much about the solution, which is reasonable because in E&M we kind of spend quite a long time in the first semester of E&M to talk about basically mathematically how do you solve Laplace and Poisson equations in different geometry, different coordinate systems. So there are lots of solution method, but so it's kind of hard to expect in one section to talk about all these. So your textbook only talk about the uniqueness property of the solution given the boundary condition, right? So supposedly you have a boundary condition specified on the surface of a volume, and the Laplace and Poisson equations becomes unique. So the Laplace equation is obviously you will talk about it already. So that's Laplace equation. The Laplacian function, the scalar function is 0. That's the Laplace equation. And then the Poisson equation is pretty much the same, except you have a inhomogeneous term or source term. The Laplacian psi is given by whatever source term, and that's the function x because Laplacian is a spatial operator, so you operate on the function psi is a function of x, and the source is also a function of x. Okay, so that's the Poisson equation, and the discussion here is just to say that it's unique given a certain boundary of a surface. So you have a volume V, and there's a surface S, right? And there are two problems that can be solved. One is solve the interior problem, the other is solve the exterior problem. But the interior problem, obviously, you just specify the boundary condition on this surface S. But the exterior problem, you have the surface S plus the surface plus the condition at infinity, and that it depends on the situation. But in most cases, we specify as x tends to infinity, it tends to 0. So that will give you another boundary condition. If not, whatever the kind of boundary condition at infinity that you may need to use that instead, say like instead of 0 is a constant, and you probably need to subtract that. Okay, so that's the boundary value problem, and for boundary value, the boundary value is specified on S. Usually two kind of boundary condition. One is given psi, so psi is given by some function specified psi S. Like if psi sub S is given on the S, that can depends on the location on the surface. But this is in a three-dimensional space. But this is a two-dimensional volume surface. So the function can depends on the location on the surface. It can be a function of x only, but the x, but then it's x is within the surface, right? That is what we call the Dirac boundary condition. So that's one thing, and the other is the other kind of boundary condition is the derivative of psi on the S, but we mostly just consider the normal derivative because the parallel derivative, you specify that might give a problem because you might not find a solution. So we usually just set the derivative on normal derivative on the surface, so it is n dot into gradient psi on S. right? And the n is the normal direction, and now you need to pay attention to the context of your problem. Sometimes it defined as pointing outward from the interior of the problem, pointing outward. Sometimes it's defined pointing inward, but either case is the normal derivative. So this is maybe give it a side as pi, something like that. That depends on x on the surface. Okay, so either and sometimes we write like partial psi partial n, right? Because it's now after you dot into that's the scalar, and then we define this n coordinate along a given normal direction. So this n is treated like a coordinate, like a x, y, z, but then it's defined as the distance from, like you can say the n is 0 on the surface, and then you define a positive when you're pointing to the direction of n and negative of direction n. This n value is negative, but n is a spatial variable. Okay, so you define as positive psi positive n. Okay, so that if you specify that, that's called a Neumann boundary condition. Okay, and sometimes in some cases you can say the part of the surface you use Dirichlet, the other part you use Neumann. That is also possible. That kind of mix, but usually you don't do it both. So you don't specify both boundary condition on S, because usually that will give you inconsistent solution, because you cannot find a solution satisfy both the Dirichlet and Neumann boundary condition. Okay, so but mix is okay. So it's part of that is Dirichlet, part of that is Neumann. That is possible. Okay, so there's the different kind of boundary condition you can set. This discussion in 9.5 is just the property that if you found a solution like size of 1 that satisfies either the Laplace or Poisson equation and the given boundary condition, either Dirichlet or Neumann or mix, then that's a solution size of 1. But if you also say that you find another solution size of 2 different from size of 1, is independent of size of 1, and satisfy the same boundary condition, then you can show that that's unique. In the sense, for the Dirichlet, they will be the same. For the Neumann, they will be different from constant. Right. So the argument is pretty straightforward. You just assume if psi 1, psi 2 are the solution of the same, satisfy the same set of boundary condition, then you can define a function. I think this psi defined as the difference between the two. Right. Then obviously, because you subtract that, the Laplacian sign must be 0, because both satisfy for if psi one side up to a solution Laplace, obviously the right hand side is 0. But even if it is Poisson equation, because they are solution of the same Poisson equation or the same source, then the subtraction, the right hand side will cancel, become 0. So the difference of these two solutions will kill the source term. So it satisfies the Laplace equation is there. So now it depends on the boundary condition, because if they both satisfy the Dirichlet boundary condition, the same value, whatever the function, even if it's function x, because you subtract the two, then the boundary condition of psi is obviously 0. So the boundary condition is psi equals to 0 on S. For the Dirichlet problem, or partial psi partial n equals 0. as for Neumann boundary condition, right? So either this or that will satisfy by this side, or mix, or part of that satisfy this and part of that satisfy that. So, right? Because whatever, even if the boundary condition depends on space has spatial dependence, after you subtract that, the boundary condition will be exactly zero. But the difference between the two solutions. Okay, then it's okay so far. So that's the argument, and now we need the what we call the green identity or green theorem. I mean, there are many different forms of the green theorem. This is one of a few different form. That's 9.88 is used by cited by a textbook, the green theorem. So on S psi plus n. That should be it. I mean, the textbook has a bold face. Looks like we make it a vector, but it shouldn't be vector because the whole equation is a scalar equation. So yeah, so this should be what I said is partial n. And then the surface area integral equals to psi plus psi plus this is dv. I mean, your textbook use d tau. Tau is the volume element. It's, right? And then plus over v is inside. Okay, so this can apply to the interior problem or the exterior problem. And it probably will change the sign of n, but it doesn't matter. It's just if it's for the interior problem, obviously it's the same v. For the exterior problem, it's the v outside this volume and all the way to infinity, and include the boundary condition at infinity. Okay, so that's the green film. Do you recognize this, or do you know how to prove it? It's actually quite straightforward. I mean, it's not proof or get it from something that you know. Start with something that you know, and then get to this. Say you need this, but then you forget about this. So you need to something that you know, and then divide it. This should be pretty straightforward, right? Because usually you remember divergence theorem, right? Divergence theorem is easier to remember, right? So although the order of deriving this theorem might not be this way, so you might start with the green identity with scalar function first, and then derive the divergence theorem, the Stokes theorem, or that, and then but it doesn't matter. So for us, it's not a proof. It's just to show that from what we know. So you know the divergence theorem is we have a divergence of a vector field A right, over volume, again using the same notation as the textbook. Right. Then this is this will go to the surface integral, and some people will add a circle in the integral sign to make sure this over the whole surface, and then that is a dot into n. Yes. So n is the unit vector, and in this particular case, if v is the interior of this surface, then this n is pointing outward. Right? You remember all this, right? That's the divergence theorem, right? Then you can apply this in reverse order, and this is a surface integral, which is this term. So you first make it to like this term first. So this one is psi. This partial psi partial n is nothing but just what I did here, n dot grad phi, or you can write in different order, grad phi dot n. Yes. Right. So this one is exactly this one, and it's now is in the form of this one, right? And then you can go back to the volume integral. What is that? This is a vector A. So we need the divergence of the vector A, which is psi, grad psi. A d tau. The text we use d tau. Okay. Now this is just divergence theorem, and this is just rewriting it in divergence theorem. Now all three terms are volume integral. So this will be true if the integram is the same from the left hand side and right hand side. So basically, you want this divergence equals to this plus that. And can you show that? This now you can see that. How do you do that? Change rule? Is it a change? Kind of like it's the product rule, yeah, product rule, but it's a vector function. So either you look up your table. They usually have lots of this vector identity or vector calculus. You can look up. So this is you look up the item divergence of a scalar function times a vector function. So, you can look up divergence of a scalar times a vector. Right. And if you look that up, you probably see that it's A divergence A plus grad A dot A. But if you are not sure about that, you can use the trick that derives it yourself using like index notation, and then you can convince yourself this is the correct identity. So now you can apply that. So this is the scalar. This is little a. This is capital A. So just this one is equals to psi divergence of the vector, which is divergence of gradient, which is Laplacian, plus gradient of the scalar, which is gradient psi dot into gradient psi, this vector gradient psi. So this equal to this plus that, which is exactly this plus that. Right. So you show that by going back to divergence theorem, then and then the vector identity, you convince yourself this green theorem or green identity is correct. Is that okay? So that's just in case that you forget and you need the green theorem. Oh, I forgot the green theorem, so you can start with this more basic thing that you remember. Okay. So that's the green identity. Now the argument is that because now you have psi is zero, partial psi, partial n, or say either this or if it makes it part of the psi is zero, part of the other part is partial psi, partial n is zero. But either way, this is zero. Right? And now for the first term, Laplacian psi is zero. So that you have a Laplacian psi here, so that's zero. So what end up is a grad psi dot grad psi, which is a square term, and then it's a positive term, or positive or zero, right? And so the whole thing must be, this one must be greater or equals to zero, but the left-hand side is zero, the first term is zero, and so the only possibility is this is exactly zero, right? And so in order that it's because it's, again it's a square term to get that to zero, so the grad psi must be zero, right? Grad psi, because it's grad psi dot grad psi must be zero, and so psi must be a constant. The whole region, it must be a constant. right? Because equals the constant. But then for the Dirac problem, if it's a Dirac problem, the psi, this constant must be psi, because psi is already 0, right? If it's 0 on the surface, psi is 0 on the surface, psi is 0 on this surface, then this constant obviously is 0, because if it's not 0, the gradient will not be 0. The gradient will be will I mean, it's not a constant. I should say, as I said, grad psi is 0, so psi must be a constant. So psi must be a constant, but already psi is 0 on the surface, so psi must be 0 for the Dirac problem. So going back to here, that implied the psi 1, that implied for Dirac, psi 1 is equals to psi 2, right? But for Neumann, it's not that, because psi is 0 is also acceptable, because Neumann just specify partial psi, partial n is 0. And if psi is just a constant, that's still a 0. Okay, so in that case, a psi 1 minus psi 2 is a constant. Right? So the uniqueness of a Neumann boundary condition is up to a constant. Other than that, the two solutions will be the same. So it's unique up to a constant. You can see that. Okay, so that's the discussion of this section. And again, this Exportian talk, at least at this in this section, not the solution, how you found solution of Laplace equation and all that. We might see some later on, but or you might need to wait for E&M to solve. There might be homework problem for Laplace equation solution, but we did some of that in like the box solution in the separation of variable discussion. So that part of the solution, but to talk about different solution for different kind of geometry is a lot of discussion. So, well, like in E&M, we spend maybe half of a semester to talk about just this, how you solve this. Okay, but anyway, that's just the discussion of uniqueness for this section. All right, any questions?